For as long as astronomers have studied Saturn, there's been one incredibly basic question about the planet that nobody could actually answer with confidence. How long is a day there? It sounds like it should be one of the simplest facts to establish about any planet, something you'd assume was settled centuries ago. Instead, it remained one of the most stubborn, frustrating, unsolved mysteries in planetary science, resisting every attempt to pin it down for decades. Then, using data gathered from Cassini's rings observations, including its final years at Saturn, scientists finally cracked it. In this video, we're going to walk through why something as basic as Saturn's rotation rate turned out to be so difficult to measure, how Cassini's ring data finally solved it, and why the answer actually matters far beyond just satisfying scientific curiosity. If you enjoy real, documented space science rather than exaggerated claims, stick around till the end. To really appreciate why this particular mystery deserves to be called one of Saturn's biggest, it helps to compare it to something we take completely for granted here on Earth. Every school child knows Earth's day is 24 hours long, and nobody thinks twice about how confidently we know that number. For Saturn, one of the largest, brightest, most easily observed planets in the entire night sky, a planet humans have been watching through telescopes for over 400 years, this same basic fact remained genuinely uncertain right up until 2019. That gap between how simple the question sounds and how long it actually took to answer is exactly what makes this such a compelling scientific story. Let's start with why this problem was so hard in the first place, because it's genuinely one of the more counterintuitive puzzles in planetary science. For a planet like Earth, figuring out the length of a day is trivially easy. You just watch a fixed point on the ground, like a mountain or a city, and time how long it takes to rotate back into view. Earth has a solid surface with permanent landmarks you can track. Saturn doesn't have that luxury. It's a gas giant, meaning what we see when we look at Saturn isn't a solid surface at all, but the top of a churning, constantly shifting atmosphere of hydrogen and helium with cloud bands that move at different speeds depending on latitude, similar to how Earth's jet streams move independently of the ground beneath them. There's no fixed landmark on Saturn's visible surface you could track to measure the planet's true underlying rotation rate, because the visible cloud tops simply don't rotate as one single uniform unit the way a solid planet would. Given this challenge, scientists had to rely on an indirect method instead, measuring the planet's magnetic field. This actually works well for most planets, including Jupiter. A planet's magnetic field is generated deep in its interior, and it's usually tilted slightly relative to the planet's actual rotational axis. As the planet spins, this tilted magnetic field sweeps around like a rotating beacon, and it produces a periodic radio signal that instruments can detect from a distance. By measuring how often that radio signal repeats, scientists can calculate exactly how fast the planet's interior, not just its clouds, is actually rotating. This technique worked beautifully for Jupiter, giving scientists a precise, confident rotation rate for that planet decades ago. Saturn, though, turned out to be uniquely uncooperative in this regard. Its magnetic field is almost perfectly aligned with its rotational axis, an alignment so close to exact that it doesn't produce the kind of clear, detectable periodic wobble that this radio signal method depends on. It's a bit like trying to determine how fast a spinning top is rotating by watching its handle, if that handle happened to be pointed exactly straight up along the spin axis with no wobble at all. You simply wouldn't see the kind of periodic motion that would let you time the rotation. This left scientists with a genuinely awkward gap in basic planetary knowledge about one of the largest, most recognizable planets in our own solar system. This wasn't for lack of trying either. NASA's Voyager 1 and Voyager 2 spacecraft, flying past Saturn in the early 1980s, made early attempts to measure this radio signal, and came up with an estimate of roughly 10 hours, 39 minutes, and 23 seconds for Saturn's day. For years, this Voyager-era estimate was treated as the best available figure, even though scientists suspected it might not be entirely accurate given the challenges involved. Then, when Cassini arrived at Saturn in 2004 and began its own long-term observations, things got more confusing rather than clearer. Cassini's instruments detected that the periodicity of Saturn's radio signal actually seemed to be changing over time, sometimes measuring closer to 10 hours and 45 minutes, other times drifting toward different values entirely, ranging as widely as 10 hours 36 minutes to 10 hours 48 minutes across different observation periods. This drift became a genuine source of ongoing frustration and confusion for the mission's scientists throughout much of Cassini's early years at Saturn. Each new measurement using the radio signal method seemed to disagree with the last, and rather than converging on a single, increasingly confident answer the way repeated measurements normally should, the numbers kept shifting around unpredictably. Cassini's own magnetometer team published several papers throughout the mission attempting to explain and refine these drifting estimates, but each new attempt only reinforced the growing suspicion that something fundamental about the measurement technique itself, rather than the underlying planet, was the actual source of the inconsistency. This was a deeply strange result, because a planet as massive as Saturn simply shouldn't be able to noticeably speed up or slow down its actual rotation rate over the course of a few years or decades. The physics involved would require an almost unimaginable amount of energy to meaningfully change the spin rate of an object that large. Scientists gradually realized that the radio signal itself wasn't a reliable, direct measurement of Saturn's true internal rotation at all. Instead, it seemed to be influenced by other factors in the planet's magnetosphere and ionosphere, things like seasonal changes and interactions with the solar wind, which caused the observed radio periodicity to drift around, even though the planet's actual rotation rate underneath all of that activity was almost certainly staying constant. In effect, the one tool scientists had been relying on to measure Saturn's day length turned out to be unreliable, leaving the fundamental question wide open again, decades after Voyager first attempted an answer. This is where the story takes a genuinely creative turn, one that had actually been proposed decades before anyone had the technology or data to actually attempt it. Back in 1982, before Cassini had even been designed, scientists first floated the theoretical idea that Saturn's rings themselves might hold the answer. The logic went something like this. Deep inside Saturn, the planet's interior isn't perfectly still. There are subtle oscillations and vibrations happening within its layers, somewhat similar to how Earth experiences seismic activity, except driven by different internal processes specific to a gas giant structure. These internal vibrations slightly affect Saturn's gravitational field, and because Saturn's rings are made of countless small particles orbiting incredibly close to the planet, they're sensitive enough to these tiny gravitational fluctuations that the vibrations actually leave a visible signature in the rings themselves, in the form of extremely subtle wave patterns rippling through the ring material. To put this in more everyday terms, imagine dropping a small pebble into a still pond and watching the ripples spread outward across the surface. Saturn's internal vibrations act something like that pebble, except the pond is the planet's own gravitational field and the ripples show up not as visible waves on a water surface, but as subtle density variations within the orbiting ring particles hundreds of thousands of miles away. Detecting these ripples requires an extraordinary degree of precision, since the actual physical displacement of ring particles caused by these gravitational nudges is remarkably small, but the fact that they're detectable at all, given how faint and indirect this entire chain of cause and effect is, says a lot about just how sensitive Cassini's instruments ultimately needed to be to make this discovery possible. As Christopher Mankiewicz himself explained it, mass inside the planet essentially sloshes back and forth, and the surrounding rings physically feel that motion through gravity, even though the rings themselves sit an enormous distance from wherever this sloshing is actually happening deep inside Saturn's interior. It's a genuinely striking image once you sit with it. A disk of countless small ice and rock particles orbiting hundreds of thousands of miles from Saturn's center, subtly rearranging themselves in direct response to fluid motion happening deep within a planet none of those particles will ever physically touch. In 1993, two researchers, Mark Marley and Carolyn Porco, who would later go on to lead Cassini's own imaging team, worked out more of the theoretical details behind this idea, proposing that if scientists could precisely measure these wave patterns in Saturn's rings, they could essentially use the rings as a kind of seismograph, listening to Saturn's internal vibrations indirectly, and from those vibrations work backward to calculate the planet's true rotation rate. The problem was that testing this idea required incredibly detailed, high-resolution observations of Saturn's rings, a level of precision that simply didn't exist with the telescopes and spacecraft available at the time. The idea remained a promising but untested theory for years, waiting for a mission capable of actually gathering the necessary data. That mission turned out to be Cassini. Over its 13 years orbiting Saturn, Cassini gathered extraordinarily detailed observations of the planet's rings, including a particular technique called stellar occultation, where Cassini would watch a distant star pass behind the rings from its point of view, flickered and dimmed as it passed through the ring material. This technique allowed scientists to map subtle density variations within the rings with remarkable precision, revealing wave patterns that had never been measured in this kind of detail before. Stellar occultation observations work because ring material isn't perfectly uniform. It has slightly denser and slightly less dense regions throughout, and as starlight passes through these varying densities, the amount of light that gets through changes in ways that can be measured with extreme precision by Cassini's instruments. By watching many different stars pass behind the rings during numerous occultation events spread across the mission's 13 years, scientists built up an increasingly detailed map of exactly how ring density varies, not just in general, but in the very specific, subtle, wave-like patterns that ring seismology theory predicted should exist if Saturn's internal vibrations really were leaving their fingerprint on the surrounding rings. Christopher Mankiewicz, a graduate student in astronomy and astrophysics at the University of California, Santa Cruz, took on the challenge of actually applying this ring seismology idea using the full data set Cassini had gathered, including observations collected right up through the end of the mission in 2017. For his doctoral thesis, Mankiewicz built detailed computer models simulating Saturn's internal structure, then used those models to predict exactly what kind of wave patterns should appear in the rings if his models of the planet's interior and its rotation rate were correct. He then compared these predictions against the actual wave patterns Cassini had measured, specifically focusing on Saturn's C ring, which is less dense and easier to analyze for this kind of subtle signal than the brighter, denser A and B rings. The result, published in January 2019 in the Astrophysical Journal, gave scientists their most confident, most precise answer, yet to a question that had eluded them for decades. Saturn's day is 10 hours, 33 minutes, and 38 seconds long. This figure was notably faster than the earlier Voyager-based estimate of roughly 10 hours and 39 minutes, and it fell within, but helped narrow down, the wide range of confusing estimates Cassini's own magnetic field data had produced over the years. Unlike those earlier, unreliable magnetic field measurements, this new figure came from directly probing the physical motion of Saturn's deep interior, essentially catching mass sloshing back and forth inside the planet and using the ring's gravitational response to that motion as a direct physical measurement rather than an indirect, easily disturbed radio signal. Linda Spilker, Cassini's project scientist, described the result memorably at the time, saying that researchers had used waves in the rings to peer into Saturn's interior, and this long-sought fundamental characteristic of the planet had finally popped out as a genuinely solid result. She summarized the entire discovery with a simple, satisfying line: "The rings held the answer." It's worth sitting with just how elegant this solution actually is, because it represents a genuinely creative piece of scientific detective work. Scientists couldn't directly watch Saturn's interior rotate, obviously, since it's completely hidden beneath thousands of miles of atmosphere. They couldn't reliably use the planet's own magnetic field either, because of its unusually well-aligned axis. So instead, they found an indirect messenger. A ring system located hundreds of thousands of miles away from Saturn's actual interior that happened to be sensitive enough to tiny gravitational vibrations that it could carry information about the planet's deep internal motion all the way out to where Cassini's instruments could observe it. It's genuinely similar to how seismologists on Earth use vibrations traveling through rock to map out our own planet's hidden internal layers, except in this case, the seismograph wasn't solid ground, but a disk of orbiting ice and rock particles. What makes this solution particularly satisfying from a scientific storytelling perspective is that it turns one of Saturn's greatest natural spectacles into a genuinely functional scientific instrument. The rings weren't just something Cassini happened to study alongside solving this mystery. They were the actual mechanism through which the mystery got solved in the first place. Few discoveries manage to combine this level of visual grandeur with this level of clever, indirect scientific reasoning, which is part of why this particular result has remained a favorite talking point among planetary scientists, explaining Cassini's legacy years after the mission itself came to an end. This discovery matters for more than just settling an old scientific argument, though. Knowing a gas giant's precise rotation rate is actually fundamental to understanding a huge range of other properties about the planet. Rotation rate directly affects how a planet's interior is structured, influencing everything from its overall shape, since faster rotation causes a planet to bulge more at its equator, to how heat and material circulate within its deep atmosphere and interior layers. Accurate models of Saturn's internal structure, composition, and even its magnetic field generation all depend on having a reliable rotation rate as one of their foundational inputs. Before this discovery, scientists studying Saturn's interior were essentially working with a persistently uncertain, wobbly foundational number, which introduced compounding uncertainty into a wide range of other calculations and models built on top of it. This new rotation rate also has implications for understanding Saturn's atmospheric winds. Scientists calculate wind speeds on gas giants by comparing the movement of cloud features against the planet's underlying rotation rate, essentially how much faster or slower the visible clouds are moving compared to the solid interior rotating beneath them. With a more accurate, more confident rotation rate now available, atmospheric scientists have been able to recalculate and refine their models of Saturn's wind patterns, potentially revealing details about atmospheric circulation that earlier, less precise rotation estimates had obscured or gotten slightly wrong. To put this in concrete terms, before this discovery, uncertainty in Saturn's rotation rate translated directly into uncertainty about wind speeds measured relative to the planet's interior. A wind speed calculation is only as accurate as the baseline rotation rate it's being compared against, so every few minutes of uncertainty in the day length translated into meaningful uncertainty in calculated wind speeds across the entire planet. With Mankovic's more precise figure now available, atmospheric scientists gained a firmer foundation for comparing Saturn's various jet streams and storm systems against the planet's true underlying rotation, allowing for more confident conclusions about exactly how fast different atmospheric features are actually moving relative to the solid body of the planet beneath them. There's also a broader scientific technique validated by this discovery, one with implications well beyond Saturn itself. The ring seismology method that Mankiewicz used isn't necessarily limited to Saturn specifically. The same basic principle, using visible structures near a planet to indirectly probe otherwise inaccessible internal vibrations, could potentially be applied to other planetary systems where direct observation of a rotation rate proves similarly difficult. While Saturn happens to be the planet in our solar system with by far the most prominent, easily observable ring system, the underlying physics behind this technique represents a genuinely new tool in planetary scientists' overall toolkit, one that emerged directly from a combination of decades-old theoretical proposals and Cassini's uniquely detailed, long-duration observational dataset. It's also worth highlighting just how long this particular scientific story actually took to unfold, because it's a great example of how some of the most important discoveries in science require patience measured in decades, not just months or years. The initial theoretical idea was proposed in 1982. Marley and Porco developed the concept further in 1993. Cassini itself didn't launch until 1997, didn't arrive at Saturn until 2004, and didn't complete its full ring observation dataset until its mission ended in 2017. The final analysis and published result didn't appear until 2019, meaning this single discovery solving one seemingly basic question about Saturn's rotation took nearly 4 decades from initial concept to confirmed answer. That's the kind of timeline that rarely gets captured in quick headlines, but it's genuinely representative of how much of real scientific progress actually works. Think about everything that had to happen in exactly the right order for this discovery to actually take place. Someone had to first have the theoretical insight decades before it could be tested. Then a mission capable of gathering sufficiently detailed data had to be proposed, funded, designed, built, and launched, a process that itself typically spans a decade or more for a flagship planetary mission. That mission, then, had to successfully operate for over a decade, reliably gathering the specific kind of high-precision ring data the theory required. And finally, someone had to come along with the computational skill and persistence to actually build the models, run the analysis, and connect the dots between a decades-old theoretical proposal and a genuinely enormous, complex data set. Any single missing piece in that chain, a mission that failed, a theory that was never proposed, a researcher who never picked up the challenge, and Saturn's day length might still be an open mystery today. This also highlights something valuable about Cassini's specific design and mission length. A shorter mission, even when equipped with similarly advanced instruments, likely wouldn't have gathered enough high-quality ring observation data across a long enough time span to make this kind of detailed wave analysis possible. Cassini's 13 years at Saturn, including its final extremely close orbits during the grand finale, gave researchers an unusually rich long-duration data set to work with, one detailed and extensive enough to finally resolve a measurement that had eluded planetary scientists using shorter observation windows and less capable instruments for decades before it. Let's address a few common questions people tend to have about this discovery. Is 10 hours, 33 minutes, and 38 seconds now considered a completely final, unchangeable answer? It's considered the most confident and well-supported measurement available today, described by scientists involved as a really solid result, but as with most scientific findings, it remains open to refinement if future missions or analytical techniques can improve on the precision even further. The core methodology, though, using ring seismology to probe planetary rotation, has held up well since this 2019 publication. Why does Jupiter not have this same rotation measuring problem that Saturn had? Jupiter's magnetic field is tilted relative to its rotational axis, similar to Earth's, which means it produces the kind of clear, periodic radio signal that scientists can reliably use to measure rotation directly. Saturn's magnetic field is unusually well aligned with its rotational axis, for reasons scientists still don't fully understand, which is precisely what made the traditional radio signal method unreliable for this specific planet. Could this same ring seismology technique be used on Uranus or Neptune, which also have ring systems? In principle, this technique could theoretically be applied to any planet with a sufficiently detailed, well-observed ring system. But Uranus and Neptune's much fainter, less prominent rings would likely make this kind of precise wave pattern analysis considerably more difficult with current observational technology, and no mission has yet gathered a dataset for either planet comparable in scale and detail to what Cassini collected at Saturn. Why does knowing Saturn's exact day length actually matter to anyone outside specialized planetary science research? Beyond its use in refining models of Saturn's interior structure and atmospheric winds, this kind of precise fundamental data about planets in our own solar system also serves as an important calibration point for the broader science of understanding gas giant planets generally, including the thousands of gas giant exoplanets that have been discovered orbiting other stars throughout the galaxy. Every additional detail we nail down about Saturn's fundamental physical properties improves the underlying models scientists use to interpret the far more limited data available for these more distant, less directly observable worlds. How did scientists rule out the possibility that the wave patterns in the rings were being caused by something other than Saturn's own internal vibrations? This was a key part of Mankovich's analysis. By building detailed models of Saturn's predicted internal structure and comparing the resulting predicted wave frequencies against what Cassini actually observed in the rings, researchers were able to confirm that the pattern of waves matched what would be expected specifically from internal planetary oscillations, rather than from other potential sources like gravitational interactions with nearby moons, which produce different, already well understood and separately cataloged types of ring disturbances. So, to bring this all together, what did Cassini's data ultimately reveal about Saturn's biggest mystery? For decades, one of the most basic facts about one of the solar system's most recognizable planets, simply how long its day actually lasts, remained frustratingly unknown, resisting every attempt to measure it through conventional means because of Saturn's featureless, ever-shifting cloud tops and its uniquely uncooperative, nearly perfectly aligned magnetic field. It took a genuinely creative solution, first proposed decades before the technology existed to test it, and Cassini's uniquely long, detailed observation of Saturn's rings to finally settle the question. A Saturn day lasts 10 hours, 33 minutes, and 38 seconds, a fact that emerged not from watching the planet directly, but from carefully listening to the subtle, gravitational whispers its rings were quietly carrying the entire time. There's something genuinely fitting about how this particular mystery ended up getting solved. Saturn's rings are, without question, the single most visually iconic feature of the entire planet, the reason most people can instantly recognize it in any photograph. For most of scientific history, those rings were studied primarily as a beautiful, complex structure worth understanding in their own right. It took Cassini's uniquely detailed, long-duration mission to reveal that those same rings were quietly encoding information about something else entirely, a fundamental property of the planet they orbit, hidden in plain sight the entire time, waiting for someone with the right theoretical framework and the right dataset to finally decode it. This story also serves as a genuinely good reminder of something easy to forget in an era of constant news updates and instant information. Some of the most fundamental questions about even the most well-studied objects in our own cosmic neighborhood can remain unanswered for far longer than most people would ever expect. And solving them often requires exactly the kind of patient, decades-spanning scientific effort that Cassini's mission, and the researchers who continued analyzing its data years after the spacecraft itself was gone, ultimately provided. If you found this breakdown interesting, make sure to like this video, subscribe to the channel, and let us know in the comments. Did you know that scientists genuinely didn't know the length of a day on Saturn until data from Cassini finally solved it in 2019? See you in the next video with another real grounded space story worth exploring.